In this video, we will study about the U2Net and then implement it in the TensorFlow framework. So hello friends, welcome to this video. This is Nikhil Tomar and you are watching Idiot Developer. Make sure to subscribe the channel and hit that bell icon for more such videos. So our first question is, what is U2Net, or you can say U2Net? It is an architecture which is specifically designed for salient object detection. Second, it is a two-level nested U-shaped architecture built using the proposed residual U-blocks. And at last, one of the main feature of that is U2Net does not use any pre-trained backbone, which makes it really light when compared with existing methods. Now next question is, what is Salient Object Detection, or SOD? It is the process of segmenting the main object from the input image by producing a high quality mask. And here you can see some of the samples where we have images and the high quality mask. If you see this animal, we have its hair. Okay, so with this high quality mask, we are able to extract the entire object along with its fine details, which is really essential in multiple applications. Now, what are the issues with existing method that the U2Net has solved? So most existing method uses pre-trained backbone such as VGG, ResNet, ResNext, DenseNet and more. And these backbones are designed for image classification. So they lack the local details and global information, which are really important for salient object detection. So using a pre-trained backbone is not as efficient as it should be. And second, these backbone architecture loses the essential high level details during the downsampling process in the initial layer. So if you have seen any backbone architecture like VGG or mostly ResNet or ResNext, what they do is they begin with a convolution layer with a stride of 2 followed by a 2 by 2 pooling. So in these few initial layer, they downsample the feature map by factor of 4. During these initial layer, we lose the high level information, which are really essential for the salient object detection. And due to the lack of these high level features, these existing architecture are not able to perform really good. Now, what are the main contribution of the U2Net? The U2Net maintain the high resolution features with low memory and computation cost. Second, the U2Net is built using the ReSidual U-block, which help in extracting features efficiently. The last is the U2Net achieves SOTA performance on 6 dataset and runs in real time with 30 FPS on 1080 Ti with a resolution of 320 by 320. Now we'll study about the main component of this architecture, that is residual U-block. So here you can see the block diagram taken from the original paper. So if you see, it has input feature map and output feature map, and if you see its entire structure, it seems like a U-Net in itself. So you can say it's a smaller version of U-Net because it is inspired by the working, or you can say the encoder decoder structure of the U-Net and the residual block. So that's why it's a residual U-block. So it's a combination of both U-Net and the residual learning. Here you can see some of the annotations where CIN means number of input channel, Cout refers to number of output channel, M refer to intermediate channels, and L refer to number of layers, or you can say the height of the this U-shaped architecture. So if you see, we begin with CIN and we apply initial convolution layer and the number of features became Cout. From there begins our U-shaped architecture. Then again we apply a convolution based normalization ReLU. Then it is followed by a number of layers with downsampling and convolution based normalization and ReLU operation. Like this, we reach the decoder part where we have upsampling, convolution based normalization and ReLU. And like this, we reach the out at the end where it is followed by an summation with the initial feature map, and we get the output of this residual U-block. So we'll use this diagram while implementation of this residual U-block. Now let's move on to the main architecture, that is U2Net. So if you see, this is the block diagram taken from the original paper. Now first point about that is it's a two-level nested unit architecture. So now I hope you are able to get it why the author says it's a two-level unit. Okay, so first of all, these blocks inside are seems to be much similar to U-Net. Okay, and the entire architecture, if you see, it's also a unit. So that is why the author mentioned this architecture as two-level nested unit architecture, and due to this feature only it get its name U2Net. Okay, and second, each of these blocks, okay, uses the residual U block, and we'll use this diagram also during the implementation, because if you see the encoder 5, 6 and decoder 5, they are a bit different from the rest of them, because during these last block there is no downsampling or upsampling layer. If you see, just green feature map refer to convolution, Bayes normalization and ReLU, because till that stage the height and width of the feature map is so small that if you downsample and upsample is, you lose the essential information. So that is why at the last author does not apply downsampling and upsampling operation. Instead the author use dilated convolution here, because here the height and width of the feature map is really small, so it would not take that much computation time to execute that operations. Now there are two variants of the U2Net. First is normal U2Net, which achieves 30 fps, and second is a U2Net Lite version, which achieves 40 fps on 1080 Ti with the input shape of 320 by 320. So that is about a short, or I can say a simple introduction on the U2Net. Now we'll implement it in the TensorFlow framework. So we start by importing all the required libraries. So here we import the OS library, then we set this variable to 2 so that we don't get unrequired messages from the TensorFlow on our terminal. Next we have imported the TensorFlow library in which we are going to implement our U2Net. After that we have imported all the layers, that is input, convolution and rest of them. Okay, now we'll start working on our architecture. So for that we are going to implement a simple convolution block. Is going to take the input feature map, number of output channel and a dilation rate. So inside this block we have our convolution layer, Bayes normalization layer and the activation function, and here we use a ReLU activation function. Okay, so this is one of the simple and basic block which we're going to use in this entire network. Next we'll start working on our residual U block. Okay, and here we have defined a function called RSU_L. So this function take the following argument. First is take the input feature map, number of output channel, intermediate channels, then number of layer. So number of layer refer to the height of this network, and here we take a rate which have a default value of 2. So rate refer to dilated convolution. So now let's move to the paper. Here you can see the block diagram of this RSU-L. It has different blocks. If you see the scheme, so blue it has downsampling, then pink one has upsampling layers. So we are going to build all these layers and implement our RSU-L block. So majorly we have a residual U block, but there are two different variations of it. Okay, so first one we have encoder 1, decoder 1, encoder 2, decoder 2, encoder 3, decoder 3, encoder 4, decoder 4. So in all these 8 blocks we are going to use our RSU-L block. Okay, and in this block what do we have? We only have a dilation layer in the mid of those encoder and the decoder blocks, and these encoder and decoder blocks uses the downsampling and the upsampling operation. If you see the upsampling arrow, so it indicates the upsampling. Okay, but if you go down, if you go to the last part, that is encoder 5, encoder 6 and the decoder 5, so here they don't have any downsampling or upsampling operation. So simply they have set of convolution layer, and here they have dilated convolution. If you see the dilation rate of 2, dilation rate of 4, then 8. Okay, because at the last the height and width of the feature map is so small that you cannot downsample them. If you downsample them, you lose all the essential information. So here the author applies the dilated convolution because the spatial dimension of the feature map are really less, so it would not take that much computation and time to execute those dilated convolutions. So first of all, let's begin with the implementation of our this RSU-L block. If you also show you this this table where it has architecture blocks and their different values. So if we see U2Net our and this U2Net light one, so it has RSU7, RSU6, RSU5, RSU4. Okay, then it has RSU4F. So this F here indicate the dilated one, the residual U block where we have dilated convolution. And if you also see, then again we have RSU4F, RSU4F, then you have RSU4, RSU5, RSU6, RSU7. So this 7, 6, 5, 4 in front of RSU indicate the height of this residual U block. Now let's move back to our residual U block. So first of all, if you see, if we have input, it begins with a simple initial convolution layer where input channel is transformed to number of outputs. So here we change the number of channel and learn an initial representation. So let's do that. So first of all, we have our initial conv. Okay, so the output of this conv block would be X. Then we have our conv block. We're going to give it the inputs, then number of output channel. Done. Now if you see the paper, this output of this layer would be added, so we are going to save its value. So we're going to say INIT feeds initial features. So we save this initial feature. Now begins our encoder. Okay, so here some part is a bit tricky, so just focus here. Okay, so what the author has done, he has implemented all those blocks, that is RSU7, 6, 5, 4 separately. But what I'm going to do, I'm going to build a simple block for all these 4 where you can just provide these values and it would work. Okay, so let's move back to our diagram and start building that. So if you see inside the encoder, we have a simple conv layer without downsampling. If you see, it does not have downsampling. It transforms those number of output channel to intermediate channels. So let's work on that. And if you see, it has skip connections. These skip connection concatenate during the decoder part. So let's do that. So first of all, we define an empty list called skip where we save our skip feature map. Then we have a convolution block. Now this time X would be the input. Then output channel would be transformed into intermediate channels. Then we say skip dot append. Now we added or appended that output of this conv block into the skip, so that later we can use them doing the decoder. Now let's move back to the diagram. So we're going to slowly progress. Okay, now if you see, we have 1, 2, 3, 4, 5. We have 5 blocks here. Okay, where we have downsampling followed by convolution, batch normalization and the ReSidual layer. So the height of the tree is not the tree, the block is 7. So we're going to say 7 minus 2 because these are 5. Okay, so this is what we're going to follow. So we're going to have a loop here for I in range. We're going to say num layers minus 2. Simple. So let's move back. There in blue we have downsampling and the convolution block. So let's follow with that. X is equals to max pool. So it's a 2 by 2 max pooling. Input would be X. Then it is followed by a the convolution block. X and number of channel are intermediate channels, that is int ch. Now X would be added to skip list. So we are done till the blue blocks. So we are done with the encoder part. In the paper, this last also refers to as the encoder only, but I am going to mention it as bridge. So for easiness, okay. So now we'll move on to the bridge part. So we're going to write bridge here. It's up to you. You can call it encoder or bridge. I usually divide the network as encoder, bridge, and decoder part. So it is much easier for me to understand things. So in bridge, we have the normal convolution layer, X as the input, then intermediate channel, and here we have a dilation rate of 2, which is defined here. So we say rate equals to rate. Now this completes the encoder and the bridge part. Now we'll come to the decoder part. Let's move. So if you see the initial layer in the decoder, okay, so first of all, okay, if you remember those skip connection, first we have this, then this, then this. So we have these skip connection from here, 1 2 3 4 5 6. So we have 6 skip connection. Now if we see, we start applying from the 6th one, then 5th, then 4th. So what we need to do, we need to reverse the skip list. So we are going to reverse the list so that we get the last one first, then the second last one as second. So like this, we're going to reverse the list, reverse the skip connections which are stored in the list. Okay. Then next, if you see, it is followed by the concatenation. Here we have, so here in the decoder, we first have concatenation, then we have con block. There's this con block. So let's do that. So we have concatenate X, and we are going to concatenate it with the first skip connection. So we're going to say skip 0. Then it is followed by this conv block. You see, here we have this concatenation, then conv block. From the diagram, it is not easy to see which one is first, but I've seen the original code and I've implemented from there. So it is first we have concatenation, then the conv block. So X would be input, then intermediate channels. Done. Now we'll reach to the next part. Here we have these pink block, 1 2 3 4 5. So we have these 5 blocks. Okay. And if you see the last one, it transform the intermediate channel into output channel. So we're going to leave that part. This would not come inside our loop. So we have 1 2 3 4 blocks we have. Okay, so 4 means 7 minus 3 remains 4. So let's do that. For I in range num layers minus 3. Inside it, if you see, first we have upsampling, then concatenation, then it is followed by concatenation. Upsampling size would be 2 by 2. So here we upsample the feature map by a factor of 2, and here we use bilinear interpolation. Interpolation is bilinear. Input would be X. Then we have our concatenation operation. X. Now we need skip connection. So if you see, we have used the initial, the first skip connection here. Then the skip would be skip I plus 1. Because this I would begin from 0, and 0th skip connection we have used, so it would be I plus 1. Then we have our conv block, X intermediate channels. So we are done with this 4 layers. Now remaining, we have this remaining last this decoder layer. So let's implement that also. So it would be upsampling. So I'm going to copy this from here. So first we have 2 by 2 upsampling, then Then we're going to concatenate it with the last feature map, that is -1. Then now intermediate channel would be transformed to output channels, because this initial feature map also has out number of channels as out, and this also. Then we're going to add both of them, and then we're going to give the output. So here we have the add operation, add, then we're gonna have x, then init features which we have saved initially at the top. Here we have saved them. We're gonna give the value of this x back. So this is our RSU-L block. Now we'll start with the implementation of our residual U block, which is used in encoder 5, encoder 6, and the decoder 5. Okay, so if I show you the table, here it says RSU4F. So here F refers to dilated convolution and 4 refers to height of the network. So if it is 4, just imagine, okay, so C will go back to the diagram. If it is 4, then these would be 3 layers here, 1 here, and 3 here. So this is how it would work. So let's work on the implementation of that. So here we have defined the function. It's going to take the input, number of output channel, and the intermediate channel. We don't have any dilation rate here, so let me just write a comment here so that we have proper space. Now we'll define we'll define the initial convolution. So this is our initial convolution where rate is 1, okay, and we say it as x0. Then we'll define the encoder. So we say encoder, and inside the encoder we have 3 layers, where first one would have a dilation rate of 1, then 2, then 4. Here you see x0 as the input, then intermediate channel, and if you see all these 3 convolution block, they has a rate of 1, 2, and 4. Now this is your encoder part. Next comes the bridge part. In the bridge we increase the dilation rate to 8, okay, because in the last part of the layer feature maps are really low, means they have less height and width, so it is easy for you to implement these dilated convolution with less computation and time. So next comes the decoder part. So in decoder part first we have the concatenation. So we are going to concatenate first x4 with x3rd, okay, then we have our convolution block, con block, x as the input, then intermediate channels, and here rate would be 4, okay. Now we're going to reverse the rate in decoder, first 4, then 2, then 1, okay. So like this we have another decoder layer. First we have concatenation with x2, then again convolution block with rate of 2. At last we have one more decoder set of layer where we concatenate the output with x1, okay, the initial con, the first layer of encoder, and here we have a dilation rate of 1. At last we are going to add the output of decoder and the initial x0, and this forms our RSU4F block, okay. So how easy it is, okay. Now if you go to the original code, there you have seen with the implementation of RSU7, 6, 5, 4, then you will see the implementation, but this is a bit complicated but easy. It shortens the number of lines of code, which makes you more productive, okay. Now we'll begin with the implementation of U2Net. So if you see, there are 2 versions of this. First is a light one and second is the main one. So we begin with our mains function here, and if you see this paper, let me show you again the table which is important. So if you see, we have this intermediate channel, okay, then we have number of output channels. So I'm going to import a list, not the list, I'm going to build a list which have these features, okay, these number of channels. Now we'll start with the implementation. of our network, and we're going to call it U2Net. Okay, first it's going to take the input shape, which would help us to define the input layer, then output channel list, the intermediate channel list, then number of class. By default we say it as 1. So first of all we define the input layer. So it would be inputs equals to input layer with input shape. Done. So for simplicity we say S0 is inputs, just for ourselves. Then we'll begin with the architecture. Okay, before that let's call it here. So first it would take the input shape. Let's provide a size of, let's say, 512 by 512 by 3. Then out channel list, then intermediate channel list. Okay, so we're done. Now we'll begin with the encoder. Let's go back. So here you see, first it is followed by RSU-7. So we say S1 as the output of RSU block, RSU-L. So it would take input as 0, output channel would be out channel 0, then intermediate channel at the index position 0, and L, if you go back here, it has number of layers, right? We don't need to define. So for layers we're gonna say 7. So this is RSU, or not here, 7. The height of the RSU block is 7. Then we have PP1, that is max pooling. So here we have a 2 by 2 max pooling. So the input would be S1. Now let me just try to print the shape of S1 and the P1 and run the architecture to see that there is not any error or any issue with this. I hope we don't have any error. So here you can see we don't have any error. So we simply get the shape. First is 512 by 512, then 256 by 256, and this is really fine because having no error is really good. Then we're gonna have decoder 2. If I go to this, not the decoder, the encoder 2, that is RSU-6. So let's do it till RSU-4. So I'll directly copy paste thing here till RSU-4. So this is S2, and in this we just do same thing, just change the inputs to these two RSUs and the max pool, and we increment the index number from 0 to 1, 2, 3. Even you can put everything in loop if you are really smart. So now let's print the shape of P4 and check if we have any error or not. Okay, so till now we don't have any error. Now we'll implement this RSU-4F, because after RSU-4 we have RSU-4F, which is repeated 3 times. So let's do it. So we're going to say S5 equals to RSU-4F. Input would now be P4, out channel would be index position 4, in channel index position 4. Done. Then it is followed by the max pooling. Max pool 2D, 2 by 2 max pooling. Input would be S5. So just when you implement it, just see if you have correct input, because things get confused and messy sometime. So this is our encoder. Now we'll implement the bridge. And in bridge also we have the same RSU-4F layer. Okay. Same, we just increment the index number here and change the input to P5. And after that it is followed by 2 by 2 bilinear upsampling. Simple. Now comes the decoder part. So in decoder, let's move to our diagram. So in the decoder, first we have concatenation. If you see here, we concatenate, then it is followed by these RSU blocks, and then we have our upsampling. So let's follow that sequence. So we're going to say D1 for the decoder 1, concatenate. So here we are going to concatenate the B2, the sample feature map, with S5. Okay. So during concatenation, the shape of these two features should be equal. That is, height and width should be equal. Number of channel can be different because we stack these two features on top of each other, where one feature is below, other one is on the top. So their height and width should be same. Number of channel, if they are different, it does not matter. So before that, let's print the shape of B2 and S5. So let's run it. Okay, if you see, both the features have same height and width and also same number of channel. But in case if number of channels are different, then it's not a problem. It would definitely work. So let's work on our concatenation operation. So it would be B2 and S5. Then it is followed by the RSU 4F. And here we change the input to D1 and we increment this 5 to 6. Then we have our upsampling. We're going to say U1 upsampling. So it's, let me copy it from here. Okay, so I'm going to copy it till here. Copying is not an issue until if you got the concept, just copy it simply, because you got the concept. When someone asks you why you are simply copying it, just say I understand the concept. Now it's not an issue. Okay, so this is our first decoder block, you can say. Now we'll print the shape of U1 just to check if everything is fine or not. Okay, so you can see we have upsampled feature map of 64 by 64 and we are fine till now. Let's implement another block, that is D2. So this time I'm going to copy it, and here first we have concatenation. So we have U1, that is upsampled feature map concatenated with S4. Okay, then we have RSU-L block, because we have repeated this RSU-4F 3 times. Now comes our RSU-L block. Input would be D2, we increment the output channel and intermediate channel, and this would be RSU4. Let's go to the diagram, the table. So after RSU4, it is RSU4F, it is RSU4, 5, 6 and 7. So this is RSU4. Then we have upsampling. So like this, we're going to have few more layers. So we're going to have RSU5, RSU6 and RSU7. So I've copied them here for you. So this is D3rd, then it is D4th, and then we have D5. So if you see, after D5 we don't have any upsampling layer. This is because we have reached the end. So if I print the shape of D5, it would be 512 by 512. You see, its height and width is as equal to the input channel. Now if you go to the diagram again, see, having paper is really important because you can implement it from there. Okay, so now if you see, we are done with the network part. Okay, now if you see, we have this as side 6, 5. So these are the output from each part of the decoder and the bridge. So we have 1, 2, 3, 4, 5, 6 mask. Okay, and after that we concatenate them and get a main mask. Okay, so decoder part we are done. So here we have side outputs. Okay, so we begin with naming as y1. Okay, so we have a simple convolution layer where output number of features would be number of classes. So here it can change from 1 to 10, 20, etc. And it would be a 3 by 3 kernel. Padding equals to same, and the input to this would be D5. Okay, we go to the diagram. D5. Okay, D5 is this. Yeah. Here in our part, this is the D5. So we're gonna take this. because our all these masks, okay, these masks are same height and width, but the output feature map of the decoder are not of the same height, and so we upsample them. But for our y1 we don't need to upsample it because it is already have a height and width of 512 by 512. So let me just check it. So y1 has a height and width of 512 by 512. So that is why we don't apply the upsampling layer here, but for next mask we apply. So let's say y2. So let me copy it. So we say y2, same number of class, number of the kernel size, padding same, but the input would be d4. Now I'll print the y2. You see it is 256 by 256. So in this case we are going to upsample it. So we are going to apply a 2 by 2 upsampling on this to make sure it has a height and width equal to the input image height and width. So like this we're gonna have y3, y4 till y6 because we have 6 side masks. Okay, 1, 2, 3, 4, 5, 6, and we upsample all those side masks accordingly. So first we have 2 by 2, then 4 by 4, then 8 by 8, 16 by 16, then 32 by 32. So now let me print the shape of all these masks. Okay, so no spelling mistake. Let's just print it. So if you see, all of them have same height and width, and number of output channel is 1 because we have one class here. If we have more than one class, then please change the number of classes and use activation function would be sigmoid, not softmax. If we have more than one class, activation function would be softmax. If we have one class, activation function would be sigmoid. Now let's go back to the diagram. If you see, if we concatenate all these, then the original the implementation I've seen, they have concatenated these side mask, get the main mask, that is S fuse, the fused mask. So we're gonna say it y0, and we're gonna say concatenate. It should be y1, y2, y3, y4, y5, and y6. Okay, now it is also going to be followed by a convolution layer, that would have number of classes, kernel size would be 3 by 3, padding would be same, input would be y0. So this is our main fused output. Okay, now at last we are going to apply the activation function on this, and here we would apply the sigmoid activation function because we have one class. If we have more than one class, then please remember to change this to softmax. Okay, so now we have both the input, that is our input layer on the top, that's this, and we have our outputs, that is y1, y2, y3 to y6. Now we can have our model. Let's build our model. So this model take the inputs and the outputs, and we return our model. So let's print the summary of this model. So finally we have implemented this U2Net or U2Net. Okay, if you see, its parameter is not that high. If I see, because I've trained a lot of network, it's good. Because it is kind of unit of units, you see, and with that structure it don't have that much parameter, and this is the normal version. And if you see, it also has a light one. So now what we'll do, we'll build two function called build unit and build unit light. Let me directly copy paste them here. Okay, so now we have implemented both the build unit and build unit light. So what you need to do is you need to provide input shape and number of classes, just that. So let me remove it and test our new functions. So we say build unit. So let me provide it just the shape, number of classes by default 1. Let's print it. It's working fine. Now let's do it with build unit light. Okay, it's also working fine. Okay, and if now you see it has less parameter when compared with the original U2Net. Okay, so you can use both the architecture accordingly. If you want implementation on an Android phone or an embedded device, then U2Net Lite would be much better than this unit, not the unit U2Net one. Okay, so we have reached the end of the video. I hope you found this video useful, and if you like the content and this tutorial help you in some way, then please make sure you like the video, subscribe the channel, and share this video on all your social media. And if you have any query, any problem, or like during the implementation, or if you have any question why we have done this, then please comment it down and I'll try to answer your queries. Sometime I may not answer some questions because like even I don't have that much free time. Okay, because now I'm trying to have 2 videos per week, and also I'm trying to write some blogs. Okay, if you so check out my website or blog idiotdeveloper.com. Okay, do check out that, and please show your support to my blog also. So at the end I want to say thank you, have a nice day.